Good afternoon. I'm Frances Hellman. I'm chair of the physics department here at UC Berkeley. And it's my great pleasure to welcome you to the annual Distinguished Robert Oppenheimer Lecture. It's been my great pleasure for the past 6 years to play a role in bringing the world's greatest theoretical physicists to the Berkeley science community through this lecture. Today is particularly special because I get to introduce one of my own colleagues, and I hope friend, Marvin Cohen, who is... Okay, that wasn't supposed to be that funny. Who is university professor of physics here at Cal and senior faculty scientist at Lawrence Berkeley National Laboratory. Before I present to you Marvin's background and his amazing research history, I want to point out that this distinguished lectureship has been brought to this community for many years now by Marvin himself. He has decided who the speakers should be, he has negotiated their often complicated calendars, and has helped to plan their visits. Perhaps most notably, he introduced every one of these distinguished speakers using his own scientific wisdom to bring unique and interesting insight into these introductions. I'm not going to even attempt to reproduce that wisdom and insight into the many connections between Marvin and the various other speakers. I will let him speak to that himself. But for managing this important event each year and maintaining the vision and the tradition of Oppenheimer himself, we owe you, Marvin, a debt of gratitude, and I'd like to hear thank you for that. This year, I felt it was time for him to give the Oppenheimer lecture. As one of the world's foremost condensed matter theorists, it was time for Marvin to shine the spotlight on his own field. Marvin was born in Montreal in 1935, came to Berkeley as an undergraduate student, graduated in 1957, went on to receive his PhD from the University of Chicago, did a postdoc at Bell Laboratories, and then, thankfully, came back to Cal as a professor. Like Oppenheimer, who in many ways is credited with making the tradition of theoretical physics at Berkeley flourish, Marvin has done the same for condensed matter theory, particularly in the area of materials physics, but more broadly. It has been for several decades one of the department's great strengths, and this has a lot to do with Marvin, both as a scientist and as a teacher. His work goes deeply into diverse topics, including predictions of superconductivity in highly doped semiconductors and high-pressure phases of silicon, elucidation of electronic and vibrational states in a wide range of important solids, including, most recently, fullerenes and carbon nanotubes. Marvin, years ago, developed the pseudopotential model, which he used to explain the structure and properties of known materials and to predict the properties of never-before-seen materials. It allows scientists to calculate what will happen to materials under extreme conditions not found on Earth, such as under the intense pressure of planets and stars, and in nanoscale structures relevant to current nanoscience and nanotechnology. He is renowned for working closely with both his theoretical and experimental colleagues all over the world, and his papers are among the most cited in all of physics. And I'm proud to count him as my colleague and my friend. He's been awarded the National Medal of Science, the American Physical Society Buckley Prize for Solid-State Physics, the American Physical Society's Lilienfeld Prize, the Foresight Institute's Feynman Prize in Nanotechnology, the Technology Pioneer Award from the World Economic Forum, the Dixon Prize, the Berkeley Campus Distinguished Research Lecturer, the Berkeley Citation, and I'm going to stop there, but the list goes on. He's a fellow and past president of the American Physical Society, a fellow of the American Association for the Advancement of Science, a member of the National Academy of Sciences, a member of the American Academy of Arts and Sciences, and of the American Philosophical Society. And now, he's one of UC Berkeley's distinguished Oppenheimer lecturers, joining a long, distinguished list of other such speakers. And I look forward to his talk today on condensed matter physics, the Goldilocks science. Goldilocks.
Thank you, Frances, and you are my friend. And I brought water so I could be like modern speakers and reach for my bottle. Okay, as you heard, I've been on the Oppenheimer Lecture Committee since its inception in 1998, and I've enjoyed the opportunity each year to welcome you and to give an extended introduction of the lecture with some personal comments about physics or Oppenheimer or about the subject of the lecture that was not usually in my field. This year, as Francis said, I didn't have to deal with the complex schedules and needs of our visiting lecturers and the job of convincing them to lecture for a general audience. This year, I only had to plan my own lecture and think about finding next year's lecture. Let me begin to say that I want to thank my department for giving me this opportunity, and I want to thank those of you who have supported this series, especially Arlene and Stephen Krieger. These past 3 years, we had lectures on particle physics with an emphasis on the Large Hadron Collider at CERN in Switzerland and the Higgs boson. Although I didn't predict the extent of the hysteria that erupted after the announcement of the discovery on Independence Day last year, I recommended these speakers just in case, because I wanted our audiences to be prepared in case this discovery was made. I should add that I've greatly enjoyed seeing one of my favorite words, physics, everywhere in the lay press over the last 6 months as a result of the CERN announcement. Today, we switch gears and focus on condensed matter physics. This is the largest branch of physics, with one foot in fundamental physics and the other in applied physics, where inventions such as the transistor have had a large effect on developed societies. More than 25 Nobel Prizes have been awarded in this field, covering achievements in basic and applied areas. In addition, condensed matter physics has strong connections to most areas of science and engineering because of its focus on sizes of energies, on size length scales and time scales that are sort of in the middle of what people study in physics. And since these sizes are of interest in many other fields, the result is that condensed matter physics is diverse and it is in a sweet spot or a Goldilocks area of science. In response to some of my condensed matter colleagues who hinted that there should be more condensed matter physics in the Oppenheimer lecture series, I decided not to focus on a single research problem that I'm working on, but rather to give you an overview of the field, a discussion of a few areas of research, some comments about what others in our department are doing, and some discussion of the future. So, what is condensed matter physics? And more broadly, what is physics? Well, if you go into Wikipedia or your favorite encyclopedia or whatever and look up physics, it says it's the branch of science concerned with nature and properties of matter and energy. Some physicists also say that it involves the study of space-time, but there are other people nowadays, and I'll mention something about this, who feel that space and time are not as fundamental as we once thought they were. Sounds strange, but we'll talk about it. The principal research fields of physics are condensed matter physics, used to be called solid-state physics, but condensed matter also includes solids and liquids, but is mostly solids, atomic, molecular, and optical physics, high energy or particle physics, and astrophysics. There are other areas, there's biophysics, there's physical chemistry, there's chemical physics and so forth, but these are the major areas that you find if you look physics up in your favorite search engine. Now, condensed matter physics and AMO are closely aligned because they do deal with the same sizes of things. But as you know, particle physics deals with the very, very small, and astrophysics deals with the very, very large. And in recent years, these two have come together because you need to know particle physics to explain the Big Bang, cosmology, things of this kind. But our colleagues in particle physics are still finding the particles, whereas in condensed matter physics, we know what the particles are. So they're getting an alphabet together so that they can make words, and we're already at the word stage, but I'll show you what our problems are. There's another division that comes in physics that you may not have heard about. There are experimentalists and theorists. The experimentalists measure the properties of nature. They make the decisions. They get the last word. The theorists explain the properties and they make predictions. And if you're lucky and your prediction is helpful, you sometimes get credit, as this man who invented the wheel said, I would have never invented the wheel if it were not for Erg's groundbreaking theoretical work with the circle. Fortunately, I work with experimentalists like Alex Zettel who do give credit to theorists. One of the most important concepts in science, and it can be argued that it may be the most important concept, is that macroscopic matter is made out of atoms. Now, the old Greek concept that goes back to ancient Greece about the smallest thing would be an atom, I think they pictured little hard balls or little structures, but our modern picture of an atom is much more complex. So, an atom has a nucleus right in that center, and that's where all the positive parts of the atom are. There are protons. For example, if this was silicon, there would be 14 positive protons. There'd be a lot of neutrons, but they have no charge. And then the electrons that are run around the atom, and that planetary picture that you see all the time isn't accurate, 10 of them are held very close to the nucleus. And so this whole thing, from the standpoint of forming a solid, is inert. There's a core, and it has a charge of +4. And then there are 4 valence electrons that are running around outside that core. But it doesn't look like planets around the sun, because these are quantum mechanical particles, and therefore they are not only thought of as particles, they're thought of as waves. So we can't tell you that an electron is exactly there, but we can predict with great precision the probability of finding an electron at a specific point in space. And you may have heard that there's a probability that you're sitting in this room, and yet there's a probability that you're still at home. And, but the probability that you're at home is very small. In the 1920s, the development of quantum mechanics was at its peak, and many of the underlying theories were developed then. And in 1929, Dirac made this challenge. He said the underlying physical laws necessary for a large part of physics and the whole of chemistry are thus completely known. And the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. And so essentially my talk is an answer to Dirac of what we've been doing in the last 85 years to try to see if we can understand solids. But you have to realize that in the 1920s, people had just really completely gotten to the point that they believe in the atomic hypothesis. Earlier, let's say around 1900, there were many people who didn't believe that atoms existed. And Einstein's work in 1905 actually helped a great deal to establish the atomic picture of what goes on inside a solid. So there were 4 big developments in his miraculous year of 1905. And the determination of molecular dimensions, he developed a theory for how to find how big a molecule is, and therefore how big an atom might be. He also explained theoretically Brownian motion. If you have dust in the air, it jumps around. And it jumps around because there are molecules, air molecules that you can't see that are moving around and hitting the dust. He also developed special relativity, and he also explained the photoelectric effect. The photoelectric effect was the work that he got the Nobel Prize for. And it has to do with light shining on a metal and electrons pop out. And the only way you can explain that is to say that the light is a wave and a particle, this duality. So this was a very important piece of work for the development of quantum mechanics. So Einstein developed some of these ideas while he was still a student. And I'd like to show you his attempts at trying to get a thesis approved. Much of this was compiled by Alex Zettel, and I also talked to Einstein historians, and this will give you a picture of what it was like to be Einstein when he was a student. He went to Professor Dr. Weber, and he said that he'd like to do his thesis on a measurement of the velocity of light using a technique called interferometry. And it's interesting that later, the first Nobel Prize to go to an American was given to Albert Michelson for doing exactly this experiment. But Professor Weber was not impressed, and he rejected this thesis. Einstein then decided on a condensed matter project. He wanted to measure the effect of heat on electrical conductance. So you take a wire, have electricity go down the wire, and then make it hot. And again, Professor Weber was not impressed. And this is a very important study in condensed matter physics. So he thought, well, if he's not going to let him work on how electrical currents go down a wire, maybe he'll let him work on how thermal energy goes down a wire. And once again, Professor Weber didn't like the paper it was written on, and he felt that it was not appropriate for a thesis. So Einstein decided to talk to Professor Dr. Kleiner. And he was naive about whether professors talked to each other about their students and gossip about their students, because Kleiner obviously talked to Weber. So when Albert decided that he wanted to work on intermolecular forces and how you go from liquids to gases and so forth, Kleiner already knew his record and said no. But fortunately, he kept going, and then this is a very interesting proposal. He proposed to investigate the electromagnetic properties of an object when it's moving. And Kleiner made a big mistake, because this is a cereal bowl that my wife gave me. A is for apple, B is for ball, C is for car, D for dog, but E equals mc squared. That could have been the Einstein-Kleiner equation. But Kleiner, he just didn't get it. So for those of you who are professors out there, when your students come to you with these outrageous ideas, remember Kleiner. So he decided to do theoretical work on this idea of measuring molecular dimensions of sugar molecules, and he wrote it up for Kleiner and for another professor, Burkhardt. They said it was too short, 17 pages, but our boy added one sentence and presented it again, and fortunately, his thesis was accepted. So for those of you who are students, you have to be persistent, and for those of you who are professors, there's something to be learned here. Now, we want to put these atoms together. Now that we believe in atoms and we understand what's going on, we want to put them together into solids. And the early work on solids was basically looking at their mechanical properties. They're solids. So you take one solid and you scratch it with another solid, and you say, this one scratched that one, so this one's harder. And people did that. And in the 1800s, they developed a scale of hardness, the so-called Mohs scale. And we still use that scale. Diamond is given a perfect 10. There's no physics that goes into this. You just scratch things. And nowadays, we try to understand these properties. And then once people believed in atoms and believed that atoms made solids, then they looked at the chemical composition. For example, table salt is sodium and chlorine atoms together. And then along came X-rays. People could X-ray all these solids and find out what their structure is, how the atoms are arranged. And solids are periodic structures of atoms. And all of this is very interesting, but it didn't really give the basic underlying reason why solids have the properties they have. And the most important experiment on solids is to measure its resistance. So if you take a battery and a wire and a meter and see how much electricity will go through a solid, you'd measure its resistance. And if you correct for the length of the solid and the cross-sectional area, you get the resistivity. And that property tells you about how easy it is for electrons to move through the solid. And you find that if you took everything in the world and did this experiment with it, that pretty much you'd have a range of resistivities that's just enormous, over 30 orders of magnitude. Copper is a good metal. It allows electrons to go through. It's a conductor, and it has a resistivity on this scale of 10 to the minus 8 ohm centimeters. That's 0.000 with 8 zeros, whereas quartz or glass, they're up around 10 to the 17th. That's a 1 with zeros plus. And it turns out that if you group materials, all the materials, you find that there are metals like copper and silver and gold, and then semi-metals, and there aren't a lot of those, bismuth, antimony, arsenic, and they lie in a certain region as far as their resistivities. Semiconductors cover a wide range of resistivities, and that depends on whether they have impurities. If you put impurities into a semiconductor, that's called doping, it changes the resistivity tremendously. And that's why semiconductors are so useful, and that's what makes your computer work or your cell phone and so forth. And then there's these insulators that don't allow much electricity to go through. So the question is, what is the concept behind this that allows materials to be so different, and what's going on inside a solid? So you need a model. And as I mentioned before, we know the particles. They're valence electrons, and then there's the nuclei or the cores. So we know there's electrons and cores. We know they interact through this 2 plus charges repel, 2 minus charges repel, plus and a minus attract, electromagnetic interactions. And we know that they're waves. So it looks like we're all set. However, there are 10 to the 23rd particles in a cubic centimeter. That's the size of a sugar cube. And you have to deal with the fact that they all interact with each other. And that's where the problem becomes interesting. And studying this little cubic, 1 cubic centimeter of a solid, and developing a theory for how these particles interact has given us theories that have been useful in many, many areas of physics, including cosmology, including many fields. To give you some feeling for how many particles that is, if you take a half a glass of water and reach in and pull out 1 H2O molecule at every second, and you kept doing it, it would take you 15 million times the age of the universe to get all of those atoms out. So there are a lot of particles, and they behave in complicated ways, and the models that you choose are very important for explaining how they interact. The most popular model, I'm going to tell you about 2 models today. The most popular model is the one I've been talking about, interacting atoms model. Take atoms, bring them together, they strongly interact, form a solid. And again, we know what the particles are, and we know what's electromagnetic interactions. So this is what you end up with. This is a schematic picture of some semiconductor. There's the nucleus, and there's the cores. Those are the atoms the electrons that are held very strongly by the nucleus, and they don't affect the solid state properties. And those valence electrons that we saw before running all over, they concentrate in bonds. So this is plus, and these are negative, and so that negative concentration of electrons holds these 2 together. And that's what holds this crystal together. If this were a metal instead of a semiconductor, these electrons would be spread all over the place. And when you put a current on, they could conduct and take electricity through. And that's the basic picture that we have. And this is the most complicated slide I have today. So don't fall asleep for the rest of the lecture. You can sleep during this slide. The point is that the electrons that are in the bonds fill quantum mechanical states. There are energy levels in a crystal, and they fill these states. And then there's a gap So if you want to take an electron from here to these upper states, you have to go over an energy gap. And if you can get into these upper states, you can conduct. So for a metal or a semiconductor, there is no gap, and all the electrons can run up there and they can conduct. If you take one of those electrons and pull it all the way up above the vacuum level, it's called, and get it out of the crystal, that's the photoelectric effect that Einstein worked on. Shine light in, take an electron, pop it out of the crystal. And the light that comes in behaves like a particle and hits the electron, knocks it out. However, for a semiconductor, you've got to jump the gap. And that's the same as getting out of this bond. You've got to jump out of the bond. So you need some energy to do that. And you have to supply light or temperature, and that will get electrons going. And that's why semiconductors have a high resistance. And with insulators, this gap is huge, and that's why they have very high resistance. Why don't all the electrons fall down to the bottom? Because there's something called the Pauli principle that says you can only put 2 electrons in every state. And that's why atoms don't fall apart, and that's why you can't put your finger through the table, even though the table is mostly vacuum. And the Pauli principle is one of the fundamental quantum mechanical principles that we work with. So we find out where the electrons are, and we can calculate what their energies are. And from that, we can predict a host of properties. And just to show you that that picture, that cartoon, is real, this is a real calculation for silicon. These are the positive cores, and here's that pile up of electrons. So the density is 24 near here, 20, 16. It looks like an egg-shaped object, and it's negative, and it holds us together. And this was the theoretical prediction, and the experimental verification of the theory came later, and it shows that this is a very good picture of what's called the covalent bond, which was one of the strongest bonds in physics and chemistry. So knowing only the number of electrons and the charges, we can construct pictures of where the electrons are, and we can answer the questions about the resistivity, the mechanical properties, optical properties, and sometimes we're referred to as quantum alchemists. And this was a picture drawn by Ross Chast, who often draws cartoons for the New Yorker. I don't know if you've seen that. And this was the cover of the Sciences. And I think it's a compliment, even though mostly we say, well, what did the alchemists know? They tried to turn lead into gold. Well, they didn't have a chance. They didn't know nuclear physics. But they had recipes. They're really our ancestors. And they found many things that were quite important for the development of both physics and chemistry. Okay, now there's another conceptual model, which is quite interesting because it's basically used in our field, but it's being used often in other fields too now. And it's called the elementary excitation model, and it's based on a philosophy called emergence, and I'll tell you about that in a moment. So this one's easy to understand. You just take a bunch of atoms, you put them together, and they make a solid. It's like a Tinker toy kind of thing. But this one takes a little imagination. So let me give you the following picture. If you take a solid and you don't ask who's in there, you just hit it with a hammer and listen at the other side, the hammer will make waves because those cores are moving. And that's a sound wave. Now remember, quantum mechanics says that a particle can be a wave. Well, a wave can be a particle. So I can call those waves particles, and they're called phonons. So the question is, can I explain the properties of this solid with this so-called fictitious particle that I made up to tell me the properties of this thing? Now let me take this a little further. If you shine light on the sample, it can make excitations, and I can measure how much light gets reflected. And I don't ask what's going on inside. I try to explain what's going on inside, perhaps with these fictitious particles. If I raise the temperature, I try to explain it with these particles. Now, you might think that this is sort of self-delusion, because you're describing everything in terms of these excitations, and you're making up a picture of what they are, and you only know that you're probing it and getting a response. And you're saying that these excitations emergent behavior. But let me give you an example. If you take a box of electrons and you remove one, now remember you've got 10 to the 23rd electrons in a cubic centimeter, so take out one. And somebody says, what did the other guys do? That's very, very complicated. But if you only think about the hole that's left behind when you take it out, since you took out an electron, the thing that's left behind should be positive, like a positive electron. So let's say there's a hole here and there's all these electrons around. Then an electron from here moves into the hole, so now you got the hole over here. Another one moves in. If you study how the hole moves, you can tell how the entire system behaves. And believe it or not, engineers in Silicon Valley are designing your computers, and they're spending their whole day on these They're spending their entire day on holes. And for them, the holes are real, and explain the properties. And as I mentioned, you can also have excitations like these vibrations and explain them in terms of particles called phonons. So, are we fooling ourselves? Well, there's a philosophy called Emergence that is based on many works in philosophy, but a principal person was Henri Bergson. And the idea was that things can emerge. I mean, we're all put together by a bunch of little things, and then all of a sudden we're alive. And it's an emergent property. And Bergson went further. He said, all we can sense, all we can know about the world are what we take in through our senses. So the only reason that I know you're out there is because light shines on you and it comes into my eyes, or I can hear you. And this philosophy was discussed very actively around the 1900. Now, Bergson was a mathematician, French mathematician, and I understand that he did some important math when he was young. And he didn't believe in Einstein's theory of relativity when it came out. So he argued with Einstein, and with a sign of intelligence, he was convinced by Einstein, and then he went out and he became a big proponent of relativity. And then he moved to philosophy and talked about the difference between emergence and reductionism. Reductionism is, I know all the particles, I know their interactions, I should be able to figure out everything. Emergence people say, no, you can't, you don't have a big enough brain, you don't have a big enough computer, something will happen and you won't be able to predict it. So he's saying, look at what you get when you excite something. So he worked as a philosopher for a while, and eventually he got a Nobel Prize in literature. So he's the kind of person you'd like to have at a cocktail party. He was a really interesting person, and he influenced Einstein. And in fact, in Einstein's theory of the photoelectric effect, the title of his paper is A Heuristic Theory of the Photoelectric Effect. And scholars of Einstein have felt that this was a more model or an emergent type approach to the theory. So we deal with these kinds of things all the time. We deal with particles that you might think are fictitious, but they explain the properties of solids, and they also explain other phases of solids. And I'll go back to that later, but I wanted to say a bit about nanoscience. And in this case, the interacting atoms model works very, very well. Some time back, the Department of Energy said they would give us more money, physicists, if we worked more with chemists. And we took the money, but we never did. And who would have thought we'd be working now with biologists? And the reason that we are, and the reason that nanoscience has broken down the great walls between our departments, and these have developed over 1,000 years at least for our universities, is because we're interested in the same kind of science. And that's partially because of the scale. I mentioned that the size scale is very important. So atoms are about 1/10 of a nanometer. A nanometer is 10 to the minus 9 meters. DNA, carbon nanotubes are in here. We have proteins and so forth. And so believe it or not, physicists, chemists, material scientists, and the rest really do collaborate. Now, I showed you a picture of semiconductors where, let's say, silicon had four nearest neighbors. Well, carbon, when you have four nearest neighbors and you form this kind of a tetrahedral bonding, this is diamond. And the electrons sort of sit in these bonds and give you this structure. But something that happens with carbon that doesn't happen with silicon is that carbon will also form three bonds, and these sort of get out of the picture, and form this hexagonal array, and this looks like chicken wire, and this is graphene. So one layer of carbon arranged in this way is graphene. If you take these bonds, they're actually stronger than the bonds here. So if you could pull on a sheet of graphene, it would be stronger than diamond. However, what happens is these sheets bind to other sheets, and this is graphite, and that's what's in your pencil lead. So when you write with a pencil, the sheets sort of rub off from one another, and that's what leaves the writing on the table. Well, it turns out that this is a very interesting area, and this is a very exciting area of physics right now. And this is a real picture using the electron microscope up in the Lawrence Berkeley laboratory. And at these vertices, there are atoms of carbon. So you want to work on these single sheets. And it was hard to get single sheets, but these two enterprising people, Geim and Novoselev, actually put Scotch tape on a piece of graphite and lifted off single sheets. And Nobel Prize 2010. And Geim goes around the world telling about all the wonderful properties of graphene, and he's right. It's the thinnest imaginable material because it's one atom thick, and it has all kinds of wonderful properties. And for the experts, I just want to say one of the most important properties is that the electrons in graphene look like they have zero rest mass. This is an equation that is used called the Dirac equation. It's for a relativistic particle. It has nothing to do with graphene, but it was developed by Dirac. And if you set m equals 0, then E squared is P squared C squared, or E is PC, and the C is the velocity of light. But in these materials, this is the Fermi velocity, 1 over 300 times the velocity of light. And these particles behave in the most interesting way. They will do all kinds of magic things for you. And IBM is hoping that they will be used for electronics. And there are many articles on how to do this. So we're working on graphene very actively. If you take a sheet of graphene and you roll it up, you make what's called a carbon nanotube. And nature does it for you. And sometimes these carbon nanotubes come out so that they are semiconductors, and sometimes they come out so they're metals. And in fact, you can put them together in such a way that you can have a semiconductor in contact with a metal. And this, remember, these are very small, and it acts just like a piece of silicon in contact with a piece of aluminum. So this was a theoretical prediction. Stephen Louis is my close theoretical collaborator. Is a postdoc, my student, and his student. So we work together often on carbon nanotubes and on graphene. And experimentally, people have found this, and they're hoping to make very, very small devices. Now, there are other very, perhaps overly ambitious things that people want to do with carbon nanotubes. Remember, I told you that graphene is very strong. So if you roll it around into a tube and pull on the end, carbon nanotubes are extremely strong. And there's a lot of money going into trying to build an elevator using carbon nanotubes as the cables. And this came from basically, well, people have always wanted to build towers to the moon. But there was an article, there was a story by Sir Arthur Clarke, a science fiction writer, and who said that if you had a synchronous satellite right overhead, it's easier at the equator than here, but picture satellite right over Campanile, then perhaps you could build a cable that goes up and down, but nothing is strong enough. So there's a big project, some of it at Los Alamos, where people are trying, this is their picture, of trying to get cables to go from the Earth up to a satellite. Our calculations show that the carbon nanotube just under its own weight is a tenth the strength that's needed, but we wish them luck. On the other hand, there are applications like this one. Carbon nanotubes, this is a schematic picture, they don't always come as a single tube. They sometimes come like Russian dolls, one inside the other, inside the other. So these cylinders are inside the other. And Alex Zettel developed a technique where you can grab one in the middle and pull it out. And since there's not much interaction between the tubes, this is almost a frictionless bearing. And it can back and forth or going around. And so he has built tiny motors using carbon nanotube. And I don't know if you can see it, but there's a carbon nanotube down the center. This is a piece of gold, and then he makes it go plus, minus, and he can make it go around. This was the first one that he made some years ago. He now makes dozens and smaller, but this one could fit on the back of a virus. So that gives you some idea of the sizes of what's involved with this. There's another kind of tube that I wanted to mention. This is a Berkeley product, theoretical and then experimental. And again, Zettel was the one who made it. And this is made out of boron and nitrogen. So instead of two carbon atoms here, you have a boron atom and a nitrogen atom. I don't know which color is which here. And these are all semiconductors and very, very useful and very interesting. So with carbon nanotubes, people have developed many applications, and they're hoping, for example, they have sensors which can detect diseases. They have in gases, and they have all kinds of, I won't go into all these applications. And with boron nitride nanotubes, they're just starting. And it turns out the boron nitride nanotubes are biofriendly. So some Italian researchers have actually put them into patients and moved them into areas where there are tumors. And boron absorbs neutrons. So they shine the neutrons in, and then these heat up and kill tumors. So there are many applications. Okay, now I said that we could do most of nanoscience with that interacting atoms model. But what about this concept of emergence, that things can happen? Magnetism is a good example. You've all picked up a nail with a magnet. If you heat that magnet up at a high temperature, the magnetism goes away. So there's a property that comes and goes. There is things that many of people in our department are working on now called topological insulators. What that is, you take a semiconductor, and it acts like a semiconductor. It does everything a semiconductor does. But because of a certain property, the surface acts like a metal. I'll say something about it in a minute. There's also another effect. If you put a magnetic field on a wire, you get very special effects, again connected with topology. And finally, I'll tell you about superconductivity when materials have no resistance at all. So the theorists in our department now are studying topology, talking to mathematicians. And I know you won't believe this, but a mathematician, if he has your attention long enough, will convince you that you can turn your donut into a coffee cup, that they're the same class. However, you can't do that. So if you've done that, if you've made a bowl, theoretically, if you calculated a property of matter, it's very robust and it won't go back into another form. Let me give you a better example. Take a Mobius strip. You've all made Mobius strips where it have one surface. You can't topologically go from a Mobius strip to a regular strip. So the idea is that there are certain states, and these are on the surface of semiconductors, that are topologically distinct and robust from the bulk states. And people have now found them, and they're trying to see whether they can get some new concepts from these properties. And in the 1980s, the quantum Hall effect was discovered. People measured the resistivity of a sample as a function of the magnetic field. They turned the magnetic field on, and they got steps. And these steps were determined by the charge of the electron squared over Planck's constant times a number, 0, 1, 2, 3, and so forth. And these are very precise and actually can give you with great precision the sizes of these constants. And that was awarded a Nobel Prize in 1985. And then they found that n could be a third. It could be a fifth. And that received the Nobel Prize in 1998. And that's because it showed that electrons could behave in such a peculiar way that it looks like they didn't have a charge E, they had a charge of E over 3. And that was mind-boggling for a while, but we now understand it. Now, one of the most mind-boggling experiments in physics, certainly in condensed matter physics, is superconductivity. And you can see this is an old slide. 1911, the first superconductor was mercury. Kamerlingh-Onnes in the Netherlands at Leiden asked his students and assistants to measure the resistance of a material as you lowered the temperature. And he had liquefied helium so he could get down to a temperature around this range. And when they lowered the temperature, all of a sudden, not only did the resistance go down, it was a good metal, but it didn't go to a constant, it went to 0. And that's a real 0. Absolutely no resistance at all. And in fact, it wasn't long after that they took a wire and started a current in the wire and cooled it down. And that current, if you calculate theoretically how long that current will last if you keep it cold, it's the age of the universe or longer. It's a very stable system. And when the current goes around, as you know, when you make a loop of wire, it makes a magnetic field. And therefore, you could take something like this with a magnetic field and take it from one place to another. In fact, I think the first trip was from Leiden to over the channel to England, where they brought a magnetic field in a superconducting circle. This was an incredible discovery. In 1911, the Solway family got the best physicists, mathematicians, chemists, etc., people, prominent scientists in the world together in a hotel in Brussels. It's the Metropole Hotel. And there's Marie Curie, easy to pick out, the only woman in the group. And there's Max Planck, who began quantum mechanics, and Sommerfeld, who was one of the fathers of my field, Rutherford, who found the nucleus, and there is Kamerlingh-Onnes. And he's smiling, because this was in the fall of 1911, and in the spring of 1911, he discovered superconductivity. And I would bet anything that he told Albert Einstein about his discovery. And over the years, Einstein struggled trying to figure out if there was a general theory of superconductivity, and most of the time concluded that it was an odd property of atoms and molecules and so forth, and no general theory would result. Einstein died in 1955, and the Bardeen-Cooper-Schrieffer theory of superconductivity was discovered in 56, 57. So he didn't see it, but he would have welcomed it. I'll say more about this in a minute. So how can those electrons go through a wire and not have resistance? They're going to bump into impurities, they're going to be scattered. And so the question came about very early that how can you explain a theory like this? And what BCS, Bardeen-Cooper-Schrieffer, did was they showed that if electrons could pair, if they could get together in pairs, this could work. So one way of describing, now you'd say, how can electrons pair? They're both negative, they should push apart. Well, they can attract each other if an electron's going through the lattice and there are these positive cores. An electron can go and pull a positive core toward it. Another electron could come by very quickly and see that positive core moving and try to move to it, and it looks like they're attracted to each other. So in fact, you can get an attractive interaction in a solid between electrons. But then where does the superconductivity come from? Well, you go to a dance and you make a deal with your partner that you're going to stay 15 feet apart, but you're going to remember who your partner is. And whenever you walk toward your partner has to come toward you. You always have to go in opposite directions. So this is what happens. Here's an electron going out this way, this blue electron, partner going that way. This one's going this way, this one's going this way. So now comes a traumatic experience of bumping into a pillar. You're dancing and you hit a pillar and you bounce off. So then you should lose energy and momentum. But you have an agreement with your partner, and your partner, even though he or she doesn't have a pillar, they have to do that. And so the momentum is always conserved and they don't lose any energy. And that's a hand-waving explanation about how a superconductor can work. Now, the problem with superconductors is they're very cold. So this is the temperature, and there's helium down around 4.2 degrees Kelvin. That's our scale. And that's very, very cold. 0 is minus 460 degrees Fahrenheit. And they got better. And by the late 60s and into the 80s, they got up to maybe 25 degrees, still cold, and always needed helium. And then Bednorz and Mueller discovered the cuprates, copper oxide systems, and superconductivity was established above the boiling point of air. This is liquid nitrogen, 77 degrees Kelvin. And then Paul Chu brought it higher, and the highest temperature superconductor is 165 Kelvin under pressure. Dry ice is around 195 Kelvin. Now, turns out that we understand, using BCS theory, all these superconductors, almost all the ones on this picture, and lead, tin, zinc, and so forth. And these are in a different class. So I'm going to call these class 1 and these class 2. We were very excited at the time because now we could see superconductivity's effects because you could do it with nitrogen. Before that, it was in a solid can and you couldn't look inside. So what this is a little bowl. It has nitrogen, liquid nitrogen, has these high temperature superconductors, the copper oxide superconductors, and these little things, these little feet are little magnets. And magnets float on a superconductor. This is a picture of a train, and many of us went around to high schools levitating trains. I personally was levitated at the University of Houston. I got on something that looked like a manhole cover, and I stood there, and they kept pouring the liquid nitrogen in. I waited and waited, finally got cold enough, and sure enough. So it happens. And this is a weird feeling, but the idea is to try to get, trains going at 300 miles an hour, levitated with no friction. And in fact, just to show you the euphoria at the time, I went over to the dance department here on campus and asked them to do the choreography of the pairing that I just danced. And they did it, and it was on a Nova show. And it was really fun to watch because the students were first rambling around, and that's when they had resistance, and then you lower the temperature. I didn't like that they pretended they were freezing with the temperature, but that's artistic license. But then they paired up, and they had colored caps, and you could see how this thing looked coherent. And a lot of fun was that this was in the Figaro, which is the French newspaper, and it was something done at l'Université de Berkeley, our official French name. So the bottom line, we were all excited, euphoric, but a lot's happened since. And first of all, one thing that's happened that's good is that in those class 1 superconductors, where you have pairing and it's induced by electron lattice interactions with Bardeen-Cooper-Streefer theory, there are no experiments left unexplained to my knowledge. Everything's explained about those superconductors. And with these, I think everyone in the field agrees that there are pairs. There are many, many theories, and some of them are really brilliant, but there's no consensus on the mechanism as to which one is the appropriate one. And so the Solway Conference got a group of us theorists together in 2008, And my wife points out that all week we look like we usually look, sort of in crummy clothes, until it was time for the picture. And everybody remembered the 1911 picture. And a few of the people were very disappointed when they asked him, well, where did Einstein stand? And they said, well, this isn't the same room. So that they didn't have their chance. And unfortunately, as you would expect, when they left, there was a cartoon at the time. I don't know if you can see what it says. It's a theoretical physicist talking to a psychiatrist saying, can we start over like from 1987? So what happened in those 20 years is that there were more and more experiments, but there was no consensus on the theory of high-temperature superconductors. So it was a little like Einstein. It was a little spooky when Einstein said there may not be a theory, but people are working very hard. So let me, with just the last part of the science, and then I'll make a few comments. Well, we do understand class 1 superconductors. And in fact, you can predict, and we were able to predict that if you take silicon and you squeeze it, it will become a metal. We could predict what the structure would be, all its properties, and that it's superconducting, and with almost no input about the material itself, just about the atom, how many electrons and so forth. And so in some sense, silicon may be the best understood superconductor, even though silicon is a semiconductor. So if you're able to explain and predict, that was completely predicted from theory, what about higher temperatures? Can you predict that? Well, what about room temperature superconductivity? Can we have things floating around, trains and so forth and so on? Can we bring the power of Niagara Falls to Berkeley with no loss? And there are many people thinking about this, but it was not the kind of thing that you had conferences about until recently, because it was almost like talking about anti-gravity, which people believe no one can ever do. And high temperature, room temperature superconductivity is a little bit in that class. But IBM last October had a conference, they called it SC at 297K. SC is superconductivity, 297K is 75 degrees Fahrenheit. And we went there, and basically the people who were working on the class 2 superconductors, these are the highest temperature superconductors, wanted to do a more Edisonian approach. Mix things together and see if they can get further, with some theoretical input, wherever the theorists could help. And for class 1, I'll just give you one example of where you should look. If you take the electron pairing interaction, what's bounding them together, and you call that strength lambda, and this is the frequency of the lattice, you take the square root of this quantity and multiply by 0.2, that's the superconducting transition temperature. So you want to make this thing as big as possible. And if you get down to fundamentals, this is just the electronic spring constant. In other words, the bonds that I showed you, how springy they are, divided by the mass of the atom. And you take the square root of this, and that should tell you whether or not you can have a high temperature superconductor. So the search for high TC, at least for this class, should focus on light masses, like you find in the first row of the periodic table, and strong bonds, like those found in diamond, or C60, soccer ball, buckyball molecules. The trouble is, diamond is an insulator, so you got to get carriers in there. And some researchers in this former Soviet Union had gotten carriers into diamond, and more recently in Russia, they got 4 Kelvin superconductors. Now it's up to 10. And if you project the experiments at this point, the temperature is around 10. But if you do this theory, you get to room temperature. And so I think that this is a very important study. And there is some research going on these class 1 superconductors. But I have to caution you with a quote of Einstein that was given to me by my son. I think he probably had a reason at the time. And it was that the most valuable tool of the theoretical physicist is his wastebasket. But we hope. Okay, so a few comments and then I'll stop. Do we do basic or applied science in condensed matter? Well, you give the same answer that you give a student who asks if light is a particle or a wave. The correct answer is yes. You do both. Often, the applied work leads to problems at a fundamental level, and they're very important. And certainly, the fundamental level leads to very important problems. And one of the best quotes is coming up. William Gladstone, who was the English finance minister and later became Prime Minister of England, said to Michael Faraday was this extraordinary experimentalist who worked on electricity and developed some of our fundamental ideas. He said, "But what is the practical use of electricity?" And Faraday responded, "I don't know, but someday you may tax it." Okay, I want to assure you that condensed matter physics is in good hands in our department. These are the theorists and these are the experimentalists, and I'll talk about the young people or new people who come in. We have Jim Analytis, who is someone coming from Stanford, and he is setting up his laboratories to make new materials, very important materials. We have Bob Bergenow, who is not a new young assistant professor, but he joined our department, and he's been doing his work, but he had another job at the same time, which he's giving up now, and he'll come back to the department full time. So we're looking for Bob to come back. Bob works on novel states of matter, and he's going to be working on high temperature superconductivity. Irfan Siddiqui has a lab which he calls quantum nanoelectronics, where he does these incredible experiments and even takes superconductors and turns them into amplifiers. Feng Wang is another experimentalist, and he works in optics, and he works with lasers and optical properties. Feng can take light and shine it on a single nanotube. A nanotube is the width, it's 1/50,000th of the width of most people's hair, of a human hair. And so you can imagine how small that is. And he can shine light on it and measure the optical properties of a single nanotube. On the theory side, our youngest person is Ashvin Vishwanath. And Ashvin is working on topology, and he's taking some of the very fundamental theories that have been developed in other areas of physics, supersymmetry, quantum field theory, and some mathematics, advanced mathematics from like advanced forms of topology, to try to get new paradigms, even beyond the two that I showed you for condensed matter. And we have great hopes for him. A POG is a professor of the graduate school. It started off being called professor in the graduate school, but they didn't like it because it was... And so these POGs are peculiar people because they have officially retired from teaching, but unlike most retired people who go off and play golf or go fishing or whatever, they come in every day and they work in the labs and they keep looking for new things. And if you talk to them, you get the impression that they're under the delusion that their best work is ahead of them. Okay, one word about the future. There are a lot of problems that are challenging in condensed matter physics. There's energy production, and storage, transmission, all the problems that we've been worrying about. We like high temperature superconductors. We want to interface more with biology. Paul McEwen, who was at Berkeley and is now at Cornell, said the whole world's a machine. And there's a big machine, and then there's little machines, and once you get down to people's bodies, you have tiny molecular machines. And these are going to be figured out by nanoscience. Biology and nanoscience are coming together. So there's all these interesting things. And so how do you predict the future? Well, Yogi Berra warned us about that. He said predicting the future is difficult. Predicting is difficult, especially about the future. May Berenbaum has written that predicting the future, even that of a scientific field like condensed matter physics, is an inherently unscientific enterprise. And that is why it has often been the province of non-scientists. However, I have heard many distinguished scientists discussing this question on panels and as individuals. And let me mention 2 points that are almost always made. The first is related to the value to society of fundamental research done now for application in the future. Our own Charles Townes has emphasized how he did not foresee the many practical applications of his invention of the laser. Repairing detached retinas, cutting steel, CD players. I mean, he was doing basic research. And at the time, who would have thought that Einstein's fundamental insights would have had such an influence on the development of nuclear energy, fission, solar batteries, GPS devices that we all use, all have a connection to Einstein's theories. The second point that's usually made, it's usually made as advice to the young people, to young scientists. They're often told, work between fields. That's where the new things are. And for example, Francis Crick was a physicist who collaborated on the discovery of the fundamental nature of DNA. And a recent example is the merging of nanophysics in areas of biology, biophysics. I agree with both of these points, but being a theorist, I want to consider a more general solution to solving all those problems up there and all future problems in physics. And my suggestion is to ask Goldilocks to convince her girlfriends to consider physics and science in general as a career. We need more diversity in physics, and I wish young girls and young women would take the Goldilocks approach when dreaming about and planning for a career. They may conclude that being a Hollywood star is too hot, being an investment banker is too cold, but being a woman scientist may be just right.
Hello? Yeah. Hello? Yes. That was charming.
Thank you.
Thank you. So we have time for some questions.
What is it about class 2 superconductivity materials, I guess it's the cuprates, that make them so unpredictable rather than the class 1s?
Well, the short answer is I don't know. If I knew, I would have a theory. But it turns out that even the normal state properties of these materials, even before they go superconducting, are unusual. And the materials themselves are difficult to work with. They're getting better. But for example, the superconducting magnets that they use at the Large Hadron Collider, those are not type 2, because they're just they're hard to control, but they're getting better and better. So we don't understand the normal state of these things, and that's why we're hoping for new theories that will tell us more about the normal state. Now, of course, we all have theories. I mean, for example, one of the theories, I have to give you an answer, is that there are these new iron-based superconductors that are in class 2. And they're not quite as high temperature as the copper oxides, but iron was supposed to kill superconductivity for various reasons, but it didn't. And one of the ideas is that instead of the electrons, these are going to be pairs, instead of them being paired by coupling to the lattice, they're paired through a magnetic interaction. In other words, they send out some kind of a magnetic wave. These can be magnons or paramagnons and so forth. There are all these elementary excitations, and perhaps they pair. And that would be one theory. And these theories are being tested now. So it's a very interesting field, and we're hoping, again, for help from the whole community on this, and it's a very active area of science. Thank you.
There's a question way in the back. You want to stand up and just try talking loudly?
Why is there a big gap between the theoretical temperatures and the current temperatures of 10 degrees? I mean, what are we doing that's so wrong?
Can you repeat the question?
Yeah, I'll repeat it. Okay. 10 degrees for doped diamond, right? So theoretically, I'm claiming that it can go up to maybe 200-300 degrees or something. So the question is, why is there a big gap? And that's because I can do it on the computer. And so I can artificially put in doping to get the charges up. But experimentally, the way they do these experiments is they have to put boron into diamond. And they're getting to limits where the boron doesn't want to go in. So I can say, well, it's an experimental problem and look the other way. But in fact, right now we're working with a group at the University of Melbourne, and they have a new way of doping and treating the surface of diamond, and we're hoping that that will help. But just to give you a perspective, these things never quite work out the way you think at the beginning. So it may be that it won't be diamond, it'll be graphite, or it'll be some peculiar form of diamond, or they'll get the impurities in a certain region. But the idea is to work on this, and so you've got sometimes to go out on a limb. In some areas of physics, like particle physics, Higgs and others go out on a limb, and maybe 50 years later they tell them if they're right. In my area, unfortunately, when we go out on a limb, a year or two later, they come with their saws, and the experimentalists, they really test us. So I hope that it's an experimental problem that people will be able to overcome, but the idea is to get people thinking about it, and maybe they can think of other ways to get around some of the problems, or think of other systems.
When you were an undergrad and graduate student, what made you choose doing condensed matter physics over other fields of physics?
I was a graduate student at University of Chicago, and I was an undergraduate here, and I hadn't taken the solid-state physics course. So when I got there, I started to take it, and it looked interesting, and I thought I was going to be a particle physicist. And I walked in to see one of these professors, and he thought I was coming in to ask about being his student, and he gave me a problem to work on for a week. So I was working on a particle physics problem with somebody else, and after a week I came back, I solved it, and so he gave me another problem. And after about a month, I realized he was running my life much better than I was. And the problems were interesting. And so that's it. I always wanted to know I wanted to be a physicist. That was never a question. Always wanted to be a physicist. But in terms of what branch of physics, I didn't know. And to this day, I like all branches of physics. And unfortunately, I haven't worked in every branch of physics, but everything that I've thought about, I enjoy.
Who was that wise man?
Jim Phillips.
What was the problem?
The temperature dependence of a semiconducting energy gap, where I had to calculate the electron-phonon self-energy of an electron in a crystal. And that turned out to then make me think later. Fortunately, he left and went off to Cambridge on sabbatical, and I got the idea that I could turn all that into superconductivity, and predicted that semiconductors could be superconducting, and that was found later, and I got a job at Berkeley.
Might be a bit naive question, but if diamonds don't superconduct because you don't have enough electrons in the transport, why isn't graphene a high temperature superconductor? Because it does have the electron transport.
Yeah, I think that graphene has a chance, but it doesn't have a lot of electrons. Graphene is unusual. Semiconductors have a small gap, metals have no gap, and insulators have a big gap. Graphene is peculiar, it has zero gap. And then when you dope it, you get carriers. But there's not a lot of them. There's something called the density of states, the number of electrons you have in an energy. In graphene, it doesn't get up high enough. But I think graphene and graphite are interesting from this point of view. And in fact, these people in Melbourne are going to be working with various forms of graphite and graphene that are basically arranged in certain structures. So the short answer to you is I think that it's got a chance, but not in its ordinary way that people are using it. It has to be changed around.
Any last words of wisdom you want to pass along to any of the, you already spoke of the goal of more young women Goldilocks types. Any last words to our audience?
I think that's the most important message I'm giving you today, is that we need their help. Thank you.
Okay, let's take it.